October 1943, somewhere over the North Sea, a crippled B-17 flying fortress limped through hostile skies, its number 3 engine trailing black smoke, hydraulic fluid streaming from ruptured lines beneath the wings. Inside the cockpit, Lieutenant Sarah Mitchell fought to keep the bomber level as German fighters circled like wolves around wounded prey. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow, I've saved something extra special for you. The B-17, named Liberty's Promise, belonged to the 351st Bomb Group, serial number 4231367, built by Boeing's Seattle plant just 8 months earlier. This particular aircraft had completed 19 missions over occupied Europe, each one bringing it closer to the legendary 25-mission mark that would send its crew home. But on this gray October afternoon, with 2 engines damaged and the navigator dead from flak fragments, survival seemed unlikely. What happened next would change everything the Germans thought they knew about American aviation technology. As Sarah struggled with the controls, her co-pilot, Lieutenant James Rodriguez, activated a system that German aviation engineers had heard rumors about but never seen in action. The Honeywell C-1 Autopilot, a marvel of electromechanical engineering that would soon become the subject of intense study by Luftwaffe technical experts. The autopilot engaged with a subtle click, and suddenly the aircraft steadied. The violent shaking that had threatened to tear the bomber apart smoothed into controlled flight. Sarah's hands remained near the controls, ready to take over, but the system held course with precision that seemed impossible given the damage the aircraft had sustained. The B-17 maintained heading, altitude, and airspeed without human intervention, buying precious minutes for the crew to assess damage and plan their survival. German fighters made 3 more passes, their cannon fire punching additional holes through the fuselage. One burst severed control cables on the port side, another destroyed the radio compartment. Yet the bomber flew on, guided by circuits and gyroscopes that compensated for damage faster than any human pilot could react. Sarah watched in amazement as the autopilot made continuous micro-adjustments, keeping them airborne despite asymmetric thrust from the damaged engines and compromised control surfaces. Liberty's Promise crossed the English coast 2 hours later, still flying on autopilot. The system had navigated them across 280 miles of open water, maintaining course within 2 degrees of the programmed heading, despite battle damage that would have forced most pilots to ditch in the North Sea. Sarah took manual control only for the final approach, landing the crippled bomber at an emergency field in Suffolk with all surviving crew members safe. But Liberty's Promise would never fly again. The structural damage was too extensive for field repairs. Instead, the aircraft was stripped for parts and components, its valuable systems salvaged for other bombers. The remarkable C-1 autopilot was removed, inspected, and returned to service in another B-17. The aircraft itself was scrapped, just another casualty in the endless grinding mathematics of the bomber war over Europe. Except Liberty's Promise had one final mission to fly. 6 weeks later, during a raid on Bremen, another B-17 fitted with components from Sarah's old aircraft took catastrophic damage from flak. The pilot was killed instantly, the co-pilot severely wounded and unconscious.
The aircraft, with its autopilot engaged, flew itself 190 miles back across Germany and occupied Holland before German fighters finally shot it down over the Eiselmeer. The crew bailed out, and the empty bomber continued flying on autopilot until it ran out of fuel and crashed into the shallow waters of the lake. German salvage teams recovered the wreckage over the next 3 weeks, working in freezing water to retrieve major components. Among the items pulled from the mud was the Honeywell C-1 Autopilot. its casing dented, but its internal components remarkably intact. Luftwaffe intelligence officers recognized the value immediately. This was the system they had heard about in pilot debriefings and intelligence reports, the American Autopilot that supposedly allowed bombers to maintain formation without constant pilot input. The Autopilot was carefully packed in wooden crates filled with sawdust and shipped by rail to the Luftwaffe testing facility at Reckling, located 90 miles north of Berlin. Here, German aviation engineers conducted exhaustive evaluations of captured Allied aircraft and equipment, documenting everything from radio frequencies to bomb site accuracy. The American Autopilot would undergo the most detailed technical examination German engineering could devise. Winter 1943, Reckling Luftwaffe Testing Facility, Mecklenburg, Germany. The recovered C-1 Autopilot sat on a workbench in a climate-controlled laboratory, surrounded by measurement instruments and German engineers who approached it with a mixture of professional curiosity and personal skepticism. Senior engineer Dr. Wilhelm Hoffmann led the evaluation team, a specialist in aviation control systems who had worked on German autopilot development since before the war. Hoffmann and his team began with non-destructive examination, photographing every external surface from multiple angles and documenting every access panel, adjustment screw, and electrical connection. They measured physical dimensions with precision calipers, weighed components on calibrated scales, and used X-ray equipment borrowed from a medical facility to examine internal construction without disassembly. The initial external inspection revealed design principles that contradicted German assumptions about precision instrument construction. Where German engineers expected delicate mechanisms requiring careful handling and frequent adjustment, they found robust components built to withstand harsh operating conditions. The casing was manufactured from aluminum alloy, not the steel Germans would have used, reducing weight without sacrificing protection for internal components. Mounting brackets showed signs of severe stress from the aircraft's final flight, twisted and deformed from impact forces, yet the internal gyroscope assembly appeared undamaged. This suggested design margins that exceeded what German specifications would have required. Extra strength built into components that added weight and cost, but provided battlefield durability that theoretical calculations might dismiss as unnecessary. When the team finally began careful disassembly, following procedures they had developed for examining captured equipment, they discovered engineering solutions that challenged their understanding of what mass-produced precision instruments could achieve. The gyroscope at the heart of the system spun on bearings manufactured to tolerances German factories reserved for laboratory equipment. Yet these components came from American production lines, turning out thousands of units per month.
Preparing and narrating this story took us a lot of time. So if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. German engineers examined the gyroscope assembly with particular fascination. The spinning rotor, machined from solid metal, balanced so perfectly that it could maintain orientation for hours without drift exceeding a fraction of a degree. German autopilot designs used similar gyroscope principles, but their systems required frequent recalibration and careful maintenance by trained technicians. The American design appeared to be self-correcting with feedback mechanisms that compensated for drift automatically. The electrical components revealed another layer of sophistication that impressed the German evaluation team. American engineers had used vacuum tubes extensively throughout the system, creating amplifier circuits that boosted weak signals from the gyroscopes and accelerometers into control impulses strong enough to operate servo motors connected to the aircraft's control surfaces. German designs used similar vacuum tube technology, but the American implementation showed refinement that came from years of commercial electronics development. Dr. Hoffmann's team documented every circuit, tracing wire paths and measuring component values. They discovered that American engineers had built redundancy into critical systems, with backup circuits that engaged automatically if primary components failed. This philosophy contrasted sharply with German design approaches that assumed proper maintenance would prevent failures, making redundancy an unnecessary luxury that added weight and complexity. The servo motors that translated autopilot commands into control surface movements demonstrated mechanical excellence that German engineers found remarkable. These motors needed to be powerful enough to move aircraft control surfaces against significant aerodynamic forces, yet precise enough to make tiny corrections without over-controlling. The American motors achieved both requirements through gear trains that showed extraordinary manufacturing precision. German engineers disassembled one servo motor completely, measuring every gear tooth and bearing surface. They found tolerances that German aviation specifications would consider acceptable only for prototype construction, not mass production. Yet these components came from regular production, standard parts installed in hundreds of B-17 bombers rolling off American assembly lines every month. The implication was sobering. American industry could manufacture precision components at scales German industry could not match. The control system logic, implemented through a combination of mechanical linkages and electrical circuits, revealed design philosophy differences that explained much about American versus German approaches. The C-1 autopilot featured 3-axis control, automatically managing pitch, roll, and yaw simultaneously. German autopilot systems typically controlled only 1 or 2 axes, requiring pilots to remain actively engaged with flight controls even when autopilot systems were engaged, splitting attention between flying and other duties.
The American approach assumed that automation should reduce crew workload as much as possible, freeing humans to handle tasks machines couldn't manage. The German approach assumed skilled pilots should always maintain direct control, with automation providing only limited assistance for specific tasks. These different philosophies reflected deeper cultural and industrial differences between the two nations. Testing protocols began in December 1943, with German engineers installing the captured C-1 autopilot in a Junkers U-52 transport aircraft that served as their test platform for captured systems. The Junkers U-52, a sturdy 3-engine transport with docile handling characteristics, provided a stable platform for evaluating foreign equipment without risking more valuable aircraft. Adapting the American autopilot to the German aircraft required fabricating custom mounting brackets and electrical connections, work that took skilled technicians 3 weeks to complete. The Americans had designed their system for installation in B-17 bombers with specific mounting points and electrical interfaces. Making it work in a completely different aircraft demonstrated both the skill of German technicians and the fundamental soundness of the American design. Initial ground tests verified that the gyroscopes spun up correctly and the servo motors responded to control inputs. Engineers checked each circuit individually, comparing performance against documented specifications they had developed during disassembly and examination. Everything functioned as designed despite months underwater and rough handling during salvage operations. This durability impressed the German team, accustomed to precision instruments that required careful treatment and climate-controlled storage. The first flight test took place on a cold January morning in 1944, with the Luftwaffe test pilot and Dr. Hoffmann aboard the Junkers U-52. The aircraft climbed to 3,000 meters, a safe altitude for testing experimental systems, and established straight and level flight over the frozen landscape of northern Germany. The pilot engaged the autopilot, and the assembled engineers waited to see if months of analysis and adaptation work had been successful. The Junkers U-52 continued flying straight and level, the autopilot maintaining heading and altitude with precision that exceeded what the test pilot could achieve through manual control. The German engineers watched instruments carefully, measuring how quickly the system responded to disturbances and how accurately it maintained programmed parameters. Over the next 2 hours, they subjected the autopilot to increasingly demanding tests. They programmed heading changes, watching how smoothly the system banked the aircraft and rolled out on the new course. They commanded altitude changes, observing how the autopilot adjusted pitch and power to climb or descend at controlled rates. They introduced artificial disturbances by having the pilot momentarily override the autopilot, then releasing control to see how quickly the system recovered and resumed programmed flight. In every test, the American autopilot performed flawlessly, demonstrating capabilities that exceeded German expectations. The system responded to disturbances within a fraction of a second, faster than human reflexes. It maintained programmed parameters with precision that varied less than the instrument error in their measuring equipment.
It continued operating reliably despite temperatures that would have caused German systems to require recalibration.
Additional test flights over the following weeks explored the autopilot's capabilities under various conditions. Engineers flew in turbulence, evaluating how the system handled gusty winds and rough air. They flew at different altitudes, testing performance from low level up to 7,000 meters. They simulated emergency conditions, shutting down engines and creating asymmetric thrust to see how the autopilot compensated. Through all these trials, the C-1 demonstrated robust performance that German engineers found increasingly impressive. The system didn't just maintain basic flight parameters, it actively compensated for changing conditions, adjusting control inputs continuously to achieve smooth, stable flight regardless of external disturbances. The feedback loops that made this possible represented sophisticated engineering that German designs had not achieved. Dr. Hoffman's team produced detailed technical reports documenting their findings, reports that circulated through Luftwaffe engineering departments and reached senior officers responsible for aviation technology development. These documents painted a sobering picture of American capabilities in aviation automation, capabilities that Germany had not matched despite years of research and development effort. The reports noted that American autopilot technology reflected mature engineering that came from decades of aviation industry experience. The United States had developed commercial aviation more extensively than any other nation before the war, with airlines flying passengers across the country and manufacturers competing to build better aircraft and equipment. This civilian industry experience translated directly into military aviation technology. Germany had focused aviation development primarily on military applications, with less emphasis on commercial aviation. The Luftwaffe had excellent fighters and bombers, aircraft that could perform well in combat. But Germany lacked the depth of civilian aviation infrastructure that had pushed American engineers to solve problems related to long-distance navigation, pilot fatigue, and operational efficiency. The C-1 autopilot represented solutions to problems that emerged from flying mail routes across America, passenger services between cities, and the endless demands of commercial operators who needed reliable equipment that worked day after day without constant maintenance. These were civilian problems that had military applications, but German engineers had never approached them from that perspective. The implications extended beyond technical specifications into operational philosophy. American bomber crews flying missions over Europe faced grueling conditions that tested human endurance to its limits. Missions lasted 8 to 10 hours, much of that time spent in unpressurized aircraft at altitudes where temperatures dropped to 40 degrees below zero. Crews wore bulky heated suits and oxygen masks, operating in an environment hostile to human life. Under these conditions, anything that reduced crew workload increased mission effectiveness and survival rates. The C-1 autopilot allowed pilots to rest during long transit flights to and from targets, conserving energy for the demanding work of formation flying through flak-filled skies and fighter attacks. It maintained precise formation positions automatically, reducing the constant small control inputs that exhausted pilots during marathon missions. It freed the pilot and co-pilot to monitor other critical systems, watch for fighters, and coordinate with other crew members. German bomber crews faced similar challenges on long-range missions, but their autopilot systems provided far less assistance. Luftwaffe pilots remained actively engaged with flight controls throughout missions, their attention divided between flying the aircraft and managing other responsibilities. This constant workload contributed to fatigue that degraded performance during critical mission phases. The Americans had engineered a solution that German aviation industry had not matched. Throughout early 1944, as the Allied strategic bombing campaign intensified and hundreds of B-17’s filled European skies daily, German engineers at Reckland continued studying the captured autopilot and its implications for Luftwaffe operations. Additional captured systems arrived from downed bombers, allowing engineers to compare different production variants and document any changes American manufacturers had introduced. Every captured C-1 showed the same fundamental characteristics: robust construction that survived crashes and combat damage. Precision manufacturing, despite mass production at unprecedented scales. Sophisticated control logic implemented through elegant combinations of mechanical and electrical systems. The consistency across units impressed German engineers who dealt regularly with quality variations between different manufacturers producing nominally identical equipment. By spring 1944, the Rechlin team had accumulated enough data to produce comprehensive assessments comparing American and German autopilot capabilities. These internal reports acknowledged American superiority in automation technology, particularly in systems integration and reliability under operational conditions. The reports circulated through Luftwaffe technical branches, reaching commanders and ministry officials responsible for aviation equipment development. The documents described American advantages that went beyond individual component quality. The C-1 Autopilot succeeded because it represented a complete system where every element worked together seamlessly. The gyroscopes provided stable reference, the accelerometers detected motion, the vacuum tube circuits amplified and processed signals, the servo motors translated commands into control surface movements. Each component performed its function reliably, and the integration between them created performance greater than the sum of individual parts. German autopilot development had focused on solving individual technical challenges without achieving this level of systems integration. German gyroscopes were excellent. German servo motors performed well. German electrical circuits functioned correctly. But bringing these elements together into a unified system that worked reliably under harsh operational conditions had proven more difficult than German engineers anticipated. The Americans had mastered this integration through years of commercial aviation experience that gave them practical knowledge German researchers lacked. The captured autopilot also revealed American manufacturing capabilities that Germany could not match during wartime. The precision components inside the C-1 required specialized machine tools, skilled workers, and quality control processes that maintained tight tolerances across thousands of production units. American industry possessed all these capabilities in abundance, with factories safely located far from any combat zone and staffed by motivated workers earning good wages.
German aviation industry faced increasing difficulties maintaining quality as the war progressed. Strategic bombing targeted key manufacturing facilities, disrupting production and forcing relocation to dispersed sites less vulnerable to air attack. Skilled workers were conscripted for military service, replaced by less experienced laborers and forced workers who lacked both training and motivation. Raw materials became scarce as Allied advances cut off supply sources and transportation networks crumbled under constant bombing. These accumulated pressures degraded German manufacturing quality precisely when the technical sophistication of required components was increasing. Building autopilots that matched American performance would have demanded pristine factory conditions, abundant skilled labor, and stable supply chains. Germany had none of these advantages by 1944, and the situation deteriorated further as the year progressed. The cultural differences between American and German engineering also emerged clearly from the autopilot analysis. American engineers designed for operational reality, accepting that equipment would be maintained by mechanics with varying skill levels, using whatever tools were available in field conditions. They built robust systems with generous safety margins, redundant components, and tolerance for imperfect maintenance. German engineers designed for theoretical optimization, assuming that skilled technicians would maintain equipment according to precise specifications using proper tools and procedures. They built systems that performed exceptionally well under ideal conditions, but proved fragile when reality failed to match assumptions. This difference in design philosophy created equipment that looked impressive in specifications, but disappointed in field service. The C-1 Autopilot embodied American pragmatism at every level. Components were slightly overbuilt, providing reliability margins that prevented failures when operating conditions exceeded design parameters. Adjustment procedures were straightforward, allowing technicians with basic training to perform calibrations using simple tools. Service manuals contained clear instructions with detailed illustrations, written for mechanics who might never have seen this equipment before. German technical manuals assumed readers possessed advanced knowledge, describing procedures in abstract terms that required interpretation by trained specialists. American manuals assumed readers needed explicit step-by-step guidance with nothing left to chance or interpretation. This difference reflected fundamentally different assumptions about who would maintain equipment and what resources they would have available. Throughout 1944, as the air war over Europe reached its crescendo, German intelligence officers collected reports about American bomber operations that confirmed what Rechlin testing had revealed. B-17 formations maintained precise spacing and timing through automatic flight control systems that reduced pilot workload and improved formation discipline. Bombers damaged in combat often flew themselves home on autopilot, allowing wounded pilots to rest or giving crews time to deal with emergencies. Some B-17s returned to England with dead pilots, the co-pilot and autopilot working together to bring the aircraft home despite catastrophic battle damage. German bombers, in similar circumstances, almost never survived, requiring conscious pilot control throughout the flight home.
The difference in survival rates reflected automation advantages that German aviation industry had not matched. Field reports from Luftwaffe fighter pilots described engaging B-17 formations that maintained perfect geometry despite intense combat. The American bombers seemingly immune to the disruption that scattered German formations under attack. Fighter pilots attributed this to crew discipline and training, not understanding that automation played a critical role. The bombers held formation because autopilots maintained programmed positions automatically, requiring no conscious pilot effort. By late 1944, with Germany's situation deteriorating on all fronts and resources stretched impossibly thin, the Luftwaffe faced stark choices about technology development priorities. Jet fighter programs consumed vast resources, promising performance advantages that might counter Allied numerical superiority. New submarine designs offered hope of disrupting Allied supply lines. Rocket programs dangled the possibility of wonder weapons that might change the war's trajectory. Improving autopilot technology competed for attention and resources against these more glamorous programs. Given limited budgets, scarce materials, and desperate strategic circumstances, German aviation authorities directed resources toward weapons that promised immediate combat impact rather than incremental improvements in existing capabilities. Autopilot development continued at reduced priority, with small teams working on refinements that would never reach production before the war ended. The decision was pragmatic given Germany's circumstances, but it meant that the technical gap between American and German automation technology would never close. American factories continued producing improved autopilot systems in vast quantities, installing them in bombers that filled the skies over Europe in formations so large they darkened the sun. German bombers, increasingly scarce and relegated to desperate missions, flew with autopilot systems that had not fundamentally improved since before the war. German engineers at Rechlin understood these realities even as they continued studying captured American equipment. The C-1 autopilot represented achievement that German industry could not duplicate under wartime conditions, regardless of technical knowledge or engineering expertise. Understanding how something worked and possessing the industrial capacity to manufacture it at scale were completely different challenges. Spring 1945 brought Soviet armies racing toward Berlin as American and British forces converged from the west. Rechlin testing facility prepared for evacuation, with engineers frantically packing technical documentation and shipping critical equipment to locations farther from advancing enemy forces. The captured C-1 autopilot, along with other valuable American systems under evaluation, was loaded onto trucks for transport south. But Germany's transportation infrastructure was collapsing under the combined pressure of Allied bombing and advancing armies. Rail lines were cut, roads were clogged with refugees. Fuel supplies dried up as refineries were captured or destroyed.
The trucks carrying Rechlin's technical treasures made it only a few hundred kilometers before running out of fuel and being abandoned as Soviet tanks approached. The American Autopilot that had traveled from a frozen Dutch lake to a German testing facility to unlock secrets of American engineering excellence ended its journey discarded beside a country road somewhere in eastern Germany. Soviet troops would eventually recover some of this equipment, shipping it eastward for examination by their own engineers. The knowledge gained at Rechlin, however, survived in the detailed reports and technical documentation that German engineers had produced. These reports proved valuable in unexpected ways after Germany's defeat. American and British technical intelligence teams swept through captured German facilities, gathering documentation about enemy weapons development and technological capabilities. They found the Rechlin reports on the C-1 Autopilot particularly interesting, not for what they revealed about American systems, but for what they showed about German engineering limitations and industrial weaknesses. The reports demonstrated that German engineers understood American technical advantages clearly by 1943, but lacked industrial capacity to close the gap. They proved that Germany's famous scientific expertise and engineering prowess could not overcome fundamental disadvantages in manufacturing capability and resource availability. They confirmed what modern warfare was as much about industrial strength as battlefield prowess, and that Germany had been outmatched industrially from the war's beginning. For American aviation engineers examining these captured reports, the German analysis provided valuable external validation of their design approaches. The Rechlin team's detailed technical evaluation confirmed that American automation technology had achieved its design goals. The precision manufacturing, robust construction, and operational reliability that American engineers had built into the C-1 Autopilot had impressed sophisticated German evaluators who approached the system with professional skepticism. This validation mattered because it came from adversaries with strong engineering traditions who had every motivation to find weaknesses in American equipment. The German reports contained no propaganda or spin, just straightforward technical assessment produced for internal use by Luftwaffe specialists. Their conclusions about American automation superiority represented honest professional evaluation by engineers who understood what they were examining. The broader lessons about industrial capacity and automation technology influenced post-war aviation development in ways that extended far beyond military applications. The success of systems like the C-1 Autopilot demonstrated that automation could handle tasks humans found exhausting or difficult, freeing people to focus on activities that required judgment, creativity, and flexibility that machines could not provide. Commercial aviation embraced these lessons enthusiastically in the post-war era. Airlines demanded autopilots that could fly long routes automatically, reducing pilot workload and improving safety. Aircraft manufacturers competed to build better automation systems, applying wartime lessons to civilian applications. The C-1 Autopilot's descendants evolved into sophisticated flight control systems that enabled reliable airline operations across continents and oceans. Military aviation advanced even further, developing autopilots capable of flying complex mission profiles automatically and integrating flight control with navigation and weapons systems to create complete combat management solutions. The foundation for all these advances was laid by systems like the C-1, which proved that automation could work reliably under harsh conditions if engineered properly and manufactured with appropriate quality control.
The story of German engineers examining the captured American autopilot represents more than just technical comparison between competing systems. It illustrates fundamental truths about innovation, manufacturing, and the relationship between industrial capability and military effectiveness. Germany possessed excellent scientists and skilled engineers who understood aviation principles as well as anyone in the world. But understanding principles and implementing them at scale in reliable products were different challenges, requiring different capabilities. American success came not from superior theoretical knowledge, but from superior industrial execution.
American engineers built on decades of commercial aviation experience that taught practical lessons about what worked reliably in operational service versus what looked good on paper but failed in real-world conditions. American manufacturers possessed industrial depth that allowed precision mass production, maintaining tight tolerances across thousands of units while continuously improving quality and reliability. These advantages proved decisive in creating automation technology that worked when needed, under conditions that defeated less mature systems. The C-1 Autopilot functioned reliably in frozen bombers at extreme altitude, in aircraft damaged by combat, in hands of crews with varying skill levels and training. It worked because American engineers had designed it to work under exactly these conditions, applying practical knowledge gained from years of civilian aviation operations. The German evaluation at Reckland confirmed what the war had proven repeatedly across multiple domains. Technical sophistication without industrial capacity to implement it reliably at scale provided little advantage in modern warfare. The nation that could manufacture good enough equipment in overwhelming quantities while continuously improving quality through operational feedback would defeat the nation pursuing theoretical perfection without industrial means to achieve it. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.